Yeah, my name's Brian. I currently work at a company called Seasoned. They do,
Oh
they
wait,
help.
I'm sorry, Brian. I think Google is asking you. I'm sorry. I think
No
I think Google is asking you for consent, so you might have to press OK. Switch over to Google. Oh, now it's going. Okay.
It doesn't ask for consent. It just tells you that you should ask people for consent if you're recording them.
Yeah.
Oh, okay. It just takes a while. Okay, we're going now. Sorry about that.
All right. I'm Brian. I work at a company called Seasoned. They help the restaurant sector, primarily shift workers, find jobs, and people who want to hire them find them. So particularly interesting sector to work in right now, given the current situation. Kind of a rough sector, but really able to help people too. So that's pretty cool. I've worked at a variety of startups through my career. And I've also been involved in quite a bit of open source starting around 2009, 2010. A colleague and I started working on things together, and eventually led to a variety of open source libraries, one of which was called When, which was one of the first userland promise implementations in JavaScript to gain a lot of popularity. Before that was Q. And then another part of that project was this library called Most, which started really around 2011, 2012, but didn't look anything like it does today. And has continued to evolve since then. It's kind of crazy to think that it's getting close to 10 years old now, since the project really started, but really it didn't look like that when it started. By the way, these are my dogs. You might hear them during the presentation, so they might try to help. So what I wanted to talk about today, and I mentioned this before we started recording, is that some of this stuff is I've never presented about before, but I hope it's going to be pretty interesting. The newest incarnation of Most is called Most Core, and so I want to tell you a little bit about the background of it, just to give you some context. And then we're going to talk about its architecture and how that led to or leads to modularity, and finally how it also leads to some interesting optimizations that we do in Most Core and in Most the 1.0 version of Most. So like I mentioned, Most started, I don't know, 2011, 2012, and didn't look anything it does today. I had this need for like an asynchronous sequence of values at the time, and there was no good solution for it I could find, I was really happy with. So I started building this thing, and it was okay. And then it went through several architectural factors and never felt quite right. And then around 2013, I came across this concept called reactive programming and functional reactive programming, and some libraries in Haskell and in JavaScript. Reactive Banana was one in Haskell, and Flapjacks was a really interesting one in the JavaScript space. It's actually a compiler. And that led to rethinking everything that Most was about, and eventually led to Most 1.0. And I think it was around 2000, probably 17, 18, probably 18, when I met Tyler and a couple other folks who were interested in Most, David Chase and Frederick Krautwald. Krautwald, and started talking about the future of Most, and they actually proposed that we should do this this refactor that led to this idea of Most core. And the idea was really based around modularity. So Most 1.0 was JavaScript prototype based. It was really hard to like let other people write new things for it, because you get into this weird situation where you know, people want to add new methods to your class because they like dot chaining, but they can't, right, without modifying the prototype, and then all of the perils of modifying prototypes kick in. And so you end up in this situation where some people write functions and some people get to write methods, right? The core team gets to write methods, or someone can submit PR. If you want to write a separate library, you have to use functions or do other, you know, things that make it harder to use. And so what is it? I don't know how many of you are familiar with Most, if you've used it or if you've heard about it, but it's the way I talk about it is it's a declarative event programming library. And some people will say it's a reactive programming library. Some people will say it's a functional reactive programming library. It's not technically a functional reactive programming library based on the original definition of that. You could call it a reactive programming library, but I think that's a confusing term for a lot of people. It doesn't convey, I think, what it does, and so I call it a declarative event programming library, because it lets you be declarative. It lets you say more about what you want to do and less about how you want to do it. And events are things that occur 0 or more times. So you can think of an event as like a time value pair, where the time is just as important as value. So for example, DOM events. DOM events are a kind of event, right? You can't really separate the time from the value. A mouse click occurs when you click the mouse button, and it has a value. And more importantly, you can't observe the second mouse event until after you've observed the first. So it's indexed or ordered by time rather than by a numeric index like an array. But you can kind of think of them as an array of time value pairs. So it kind of looks like this. The what, not how part. If you want to say, I'd like to know about the mouse events until there's a click on the document, we try to design the API so that you can say you want to see all the mouse move events until there's a click on the document. So far that's worked out great. You can program in sort of either style here. The API is curried, so you get some nice benefits from that. But we think this makes a pretty intuitive way to write these kind of programs. There's a section in the Most core docs that I think is pretty helpful. You can check it out after the presentation. It talks about a little bit more about what an event is and what an event stream is, and how they work sort of conceptually, and also how they work concretely in Most. So that definition of event, a sequence of time value pairs, leads us to how we think of reactive programming in Most.js, and it's this: program that change state by reacting to events in their environment. And that pretty much, if you're writing a front-end application, this is what we're doing, right? And it's not just front-end. If you're writing like a WebSocket backend, this is very applicable. If you're doing anything with like pub sub or event buses. This is very relevant for backend as well. There's plenty of examples at these at the repo we have in the Most.js org. I'm just going to go a quick one right now. I'm not going to go too far into it. There's also, of course, a to-do MVC because everybody writes to-do MVC. So, but there's some front end and there's also a back end example at this link. So I'm going to try to switch my screen to something else, and we'll see what happens. You all see my browser?
Yep.
Great. Okay, so this is the examples repo. There's a few here. There's also some in the main Most.js most core repo. So I'm just going to show a simple one, and then I'm going to show you just briefly the code. So this is a very simple calculator. It just adds two numbers, but you can see, as I'm typing, the answer is changing. And so this is the mental model, right? Programs that react to events in their environment. So this program is very simple, but it's doing just that. It's reacting to events in its environment. All right, so what does that code look like? I'll make this bigger. This is the whole program for that little add inputs example, and the key part really is lines 16 through 23. There's an HTML page with all the DOM already in it, but line 17 says, hey, take the input events from this input element, map them to a number because they're all strings to start with, but also start with the value 0. So before there have been any events, emit a 0 event. And then the same thing for y, we just do it for different inputs. So those are the two inputs that I was typing into. And then the result value is just the addition of all the latest events from each of those. So you can kind of think of result as like the live current value of x plus y, right? It's not a one-time value. It's the value whenever x or y changes. So again, we like to let you say what, not how.
I have a quick question.
Sure.
What is the type of x and y there?
Yeah, the type is stream of number.
Okay.
We'll get more into looking at types later. Good question.
Okay.
All right, cool. And you've probably heard of or you may be familiar with other libraries, reactive programming libraries in JavaScript or TypeScript or even other languages. But there are some things about Most that we think make it interesting, that maybe are different or unique about it. And these are some of those things. We really try hard to make the API small, intuitive. It's functions first, it's curried, and it has a very simple, well-defined architecture that makes all of these things work, and we're going to dig into that. It also has some what I'm calling here novel features. They were novel when they were implemented. I don't know if other libraries do these things. I do know that some other libraries have learned from some of the things that Most has done, and of course Most has learned from other libraries as well. So it's it's not just that Most is this great thing that everybody learns from. It's a two-way street. But these are some interesting things that we think are pretty novel. And I'm going to dig into each one of these. And then probably the last thing on this list is what a lot of people know, who are familiar with Most, know it for. One of its goals from the beginning was high performance, and we think we've achieved that. There are certainly other libraries that have, that now have improved their performance, and while Most, as far as I know, is still, one of the most performant, fastest, and lowest memory, there are others certainly now are close. So we're going to start with Most's architecture. On the previous slide, I said it had a well-defined simple, well-defined architecture. What does that mean? Well, it fits on a slide, so that's hopefully saying something. This is everything you need to know about Most's architecture. There are really 3 important types. That's a lie. There are 4. One of them is not really represented here, but the first is the stream type. It just says one method, run. And the second one is called sync. And the third one you really don't need to know about here too much, just disposable. It just represents some scarce resource or something that needs to be reclaimed later or freed. And it's really stream and sync that form the foundation of everything in Most.js. All the companion libraries, third-party projects, everything. So sync is a thing that consumes events. And it's pretty obvious from, I think, from its method signatures that that's its job, right? It returns void. So stuff goes in, nothing comes out. And it does something, hopefully, interesting with those events. And then stream is the other, the producer analog of sync. And it's not as clear, I think, from the interface, but if you look at the first parameter, it takes a sync in its run method. And so if you sort of checked out in your mind, you can see it's going to do something with that sync, right? It's going to feed it something, some events. And so that's why stream is a producer of events. Then there's this other parameter, scheduler. We're going to dig a little bit more into that. It's one of the more interesting things, the more interesting internals in Most.js. And we'll talk about why. Like I said, those 2 things, sync and stream, turned out to be an incredibly flexible pair of things. We've used them, and other people have used them to build everything you can imagine. It's pretty amazing to see. You can build imperative adapters that allow you to put events in from the outside, so you can integrate with libraries like React. There's DOM events, XHR with cancellation, animation frames. You can even build another concept from React, from functional React programming, continuous values. Turns out you can build those with this stream sync idea. So it's turned out, I think we knew this going in, but it's turned out to be an incredibly flexible architecture. And that leads us to modularity, which this architecture, one of the things we've learned about it is because it's so flexible, it enables this high degree of modularity. And I, of course, stole this from Wikipedia, this definition, but I think it's actually a pretty good definition. It really speaks to what happens in Most.js with these two components, stream and sync. You can put them together in a lot of different ways and get lots of different things. The most obvious way to put these 2 things together, I've kind of already mentioned it, is you hand a sync to a stream. and the sync gets whatever events the stream wants to produce. And that's pretty obvious from the type signatures of stream and sync. But it turns out that if you do it the other way around, things get a whole lot more interesting. If you smash a sync together with a stream in this configuration, where you have events coming into a sync, and then on the other end, you have it producing events, you can do a lot. And in this case, this is kind of like the identity function, right? For a sequence of event time value pairs. It's not transforming them in any way, it's just letting them pass through. But what if you added a function to that mix? If you have events of value type A coming into the sync, and you a function from A to B, you can have a stream on the other side producing B's. Or if you have a predicate, you can smash that together with a sync of A's and a stream of A's, and you can get filter. So you've got events of A coming in on the left, and you've got maybe fewer events going out on the right. And then once you can do that, you can start putting these things together in different ways. And we're sort of popping up a level of abstraction, right? We can build the boxes. Now what can we do with the boxes? Well, we can put them together. And we can do things like map and then filter. Or we can put them together in parallel. We can take a stream, events of type A and events of type B, merge them together into a stream of A's or B's, preserving their time values. Or we can even put in a function in that case too. If we have a function that takes an A and a B, returns a C, we can take some events of A, some events of B, run them through that function, and then we get a stream of C's. And this is exactly the example we saw in that instance. This is the operation that it was using. So I have a question for all of you. Tyler mentioned that there's a good bit of functional programming at SimSpace. And I'm wondering if anybody recognizes this construct.
Lift A2, like the applicative combine.
That's exactly right. Yep, it's the applicative lift A2. Yep. Nice. So you can put things together in some really interesting ways. And that's basically how you build applications with Most.js and other reactive libraries too, is you put these things together in series, you put them together in parallel, and you build a graph of nodes. And events flow through this graph, and they're transformed and filtered and combined. And so, input events coming in on the left, and output events are coming out on the right, and maybe you're rendering them to a virtual DOM and updating the virtual DOM, or sending them out on a WebSocket or whatever. And so far this sounds great, like a perfect world. You can just build these boxes and put them together however you want, and you end up with an application that just magically works. But we're not quite there. There are some things that that hinder modularity and can trip you up when you're building these graphs and building applications with Most. And we're going to start with one of them that goes back to JavaScript promises. And if you've worked in JavaScript at all, I'm sure you've encountered these. So does anybody know what this log is? Let's say P is a promise that definitely fulfills with a value. We just don't know when. Silence.
I mean,
yeah, so the important thing here is that it cannot log world hello. It always logs hello world, even if P is like promise.resolve of of some value. It must log hello world, and the reason for that is that side effects, we don't want them to be reordered based on what P is. If someone hands you a promise, and you write a little program like this, if someone hands you P, right, you should have some sort of guarantee that side effects are going to happen in some predictable order, and it won't change depending on the P that they give you, right? So the guarantee promise make is that something like this will always log hello world and will never log world hello. Because side effects. So when you think about events in the Most.js world, they're very similar to promises, except they have multiple values, right? It's a stream of values rather than a single value like a promise. This guarantee is just as important in that world, and it's important for the very first event. So if we write sort of the analog, right, in Most.js, it looks like this, where you might cause a side effect based on a stream, and you want that a program like this always log hello followed by 0 or more world, rather than any possibility of world being logged before hello. And this is unique, as far as I know, to implementations that are similar to Most.js, push-based implementations. This was certainly unique when Most did it originally, and I think it's still unique that other similar libraries don't make this guarantee. You can construct event streams that break this rule, and that creates refactoring hazards. So if you have a graph like this, and you take one of these nodes and you move it in the graph, you refactor the graph, you could be changing the asynchrony characteristics of that graph, and there could be assumptions in later nodes that no longer hold if you changed it from a synchronous first event to an asynchronous, or an asynchronous to a synchronous first event. So Most makes this strong guarantee that run will never produce an event before it returns. And that's just a way of saying that it has to propagate the first event asynchronously. And the way it does that is using scheduler, this parameter that I didn't show on the architecture slide before. I didn't show the type of it. And I'm not really going to get into the type of it in this talk. You can look at the code. It's, to be honest, it's some of the worst code in Most.js. It's been around a really long time. It's kind of gross, but it works great. And someday we'll refactor it. And so there's just a quick look at how it works is one of the simplest event streams in Most, this stream called at, which just takes a time and a value and produces one event at that time, of that value at that time. And this is what its run method looks like. And you can see that it takes a scheduler, and then on the far right, it does something with that scheduler, right? Basically, it schedules the propagation of the event at the time, this time, using scheduler. Cool. So, so there's one barrier down, right? Async, the sometimes sync, sometimes async problem. If we take that out of the equation, now we have more modular nodes that we can move around our graph, because async is this async start versus sync start isn't a problem anymore. Cool. What about errors? Errors are one of those things, you know, if you like to program with function composition, that in some languages like Haskell, you don't have to worry about too much, because you usually represent errors in the types, right? You return an either. But in the JavaScript world, we know that any line of code might throw an exception. So we have to deal with the reality of exception propagation. And in Most.js and in some other reactive libraries, this graph is actually directly corresponds to the function call stack, the runtime call stack. And I don't mean it's kind of like the runtime call stack. I literally mean it directly correlates to the runtime call stack. So if you have an exception that occurs in one of these nodes, you know, you really are 2 levels deep or n levels deep in a call stack, and that exception is going to unwind that call stack back up the graph. And then if there's nothing there to catch it, right, your program's going to crash. So one way you can handle that is to just treat these like function calls and put a try catch there. Okay. But what ends up happening is you just end up wanting to put try catch everywhere in these, in every single node, because you don't know what the node before or what the node after is doing, or you don't want to think about it, or you want to be safe in the face of refactoring. So the only safe thing to do in that case is to just put try catch everywhere. And that kind of stinks, because one, it's messy, right? Try catch, it's statement based. You can't write arrow expressions. It's also gets de-optimized by a lot of VMs. So any function body, it used to be any function body in V8 that contained a try catch statement or try finally was automatically de-optimized by V8. And I don't think that's the case anymore. I haven't really kept up on state-of-the-art V8 optimization, but there's certainly still lots of cases where try catch can't be optimized. So, you know, if one of our goals is performance, we really don't want this. So what do we do? Well, another role that the scheduler plays is as sort of an error backstop. And you saw in the example of code from the at event stream that it was scheduling an event, and that event is run by the scheduler. And because the scheduler runs events, we can move a catch up to the scheduler and have it catch all of all of these errors, for any of these nodes. But then what do we do? What do you do with the error once we get it? If we go back and we look at the sync interface, one of the methods is error. And it looks very similar to event, except that it takes a time value and error instead of a value. So what the scheduler does, if it catches an error like this, is it sends it back through the graph, but this time using the error method. You can think of these as like channels, right? Within each of these errors, there's actually multiple channels. And one of them is the event channel and another is the error channel. And so the scheduler can send this event back through the graph in the error channel. And there are combinators in Most for catching these errors as they propagate forward again through the graph. So there's one called recover with, which allows you to provide a function for recovering from an error. It takes the error and returns a new string. All right, so cool. Problem number 2 down. Now errors aren't a barrier to being able to build and refactor these graphs. So we've got one more that I want to talk about, and it's time. Being functional programmers, you're probably all aware that wall clock time, system time, is not referentially transparent. It's hard to test. Even if you don't care about referential transparency, it's also just a pain to deal with, right? It's hard to test. It gets even trickier when you're dealing with a system like this that is specifically designed to address time, right? Time is an important component of every event in a system like this. And so dealing with wall clock time could be really difficult. And here's why. So if you ask what time is it, and you have an operation like at, and you have some node after at, it's pretty obvious what the time is, right? If at 0, then the time in the next node is still 0, because we actually represent time explicitly in the parameters to sync. We don't rely on date.now or anything like that inside of each node. But what if you refactor your graph and you introduce a delay of, say, 3 milliseconds between the at and this box? What does that mean? And what if that box did some sort of computation that used time? What would happen? You could change that calculation just by inserting this node after at and before your box. And we don't want that, right? We want to be able to snap these boxes together without that kind of, the chance for that kind of problem. But it's not clear, oops. But it's not really clear what the answer is here, or at least it wasn't for a long time. But then we had sort of a revelation. I don't know how long it's been now, maybe a year or so, that really what we want is every node to have its own concept of local time while still preserving some notion of overall time in the graph. And what that would let you do is implement the logic inside of these nodes without worrying about where they are in the graph or where you might move them to. Right? So that's what we want, right? We would love to be able to have that kind of scenario because it frees us from problems during refactoring and building the graph related to time. The question is, how do you do that? If you think of events as a coordinate system, right, where we have time on the bottom axis going left to right, and values on the vertical axis, events are points, right? There's some value at time 3, there's some value at time 4, no value at time 5 in this particular event stream, value at time 6, and a value at time 7. Right, we can think now with our goal in mind of a global time and a local time, right? We can think of this as these events occur at global time 3, 4, 6, and 7. And what we can do is create a local coordinate system for each node in the graph by creating a relative scheduler, a scheduler that's relative to the top level scheduler. Then the time with respect to the relative scheduler can start at 0. And so every box in the graph can have its own local view of time that always starts at 0. And there can still be a global clock, if you will, that also starts at 0, but it starts at 0, you know, when your program starts. And we do that with a simple idea. If you've done any graphics programming, this is a very similar concept to what you find in graphics programming. You have coordinate systems and you create transformations between those coordinate systems. And so that's what we do in Most, is we have a scheduler, a root scheduler, and then we have the ability to create relative schedulers that are relative to the root or relative to some other relative scheduler. And you can end up with a whole tree of these relative schedulers. We try to do that in an efficient way where we're not literally creating one scheduler per node in the graph. We only create them where we actually need to, where there would be a change in time, like the delay you saw. So what that does is that, you know, sort of makes time referentially transparent in the graph, right? Every node has its own local time that's guaranteed to start at 0. You can move these nodes around and not get into weird situations where your code breaks because you moved a node and the time value changed. Awesome. So we now have, you know, this highly modular graph of things we can put together and build applications. And so that's what people do. They build these huge graphs of nodes to build applications, and they get really, really big, really fast. In a large application, you know, hundreds, thousands of nodes in a graph like this. So why the scary face? Well, remember that the stream graph directly corresponds to the runtime call stack. So a very deep graph means a very deep call stack. A very wide graph means a wide call stack. In general, a big graph means lots of function calls. And again, if one of our goals is performance, we'd really love to minimize the number of function calls it takes to propagate an event from where it originates in the graph all the way, from the input to the output. And that leads us to this final topic of optimization. And again, I think this is probably something that Most is known for. I've never presented on this stuff before, so I think I hope this turns out to be pretty interesting. There's we've been looking at these graphs, and maybe something that hasn't been obvious about the graphs so far is that there are really two phases to how these graphs work, or how they're used. And the first phase is construction. You have to build the graph. And as you build the graph, it's static. It's not doing anything. It's just a bunch of nodes. And until you call run, there's no events flowing through it. It's just a representation of what will happen if you run it. It's like a machine, and you haven't turned it on yet. And then there's this other time period, which is the runtime execution of the graph. After you built the graph, then you run it. You give it a scheduler, you give it a sync, and you run it. And this distinction gives us an opportunity. It gives us an opportunity to modify the graph before it's executed. And what we'd really love to do is take a big graph and make it smaller, because smaller means fewer function calls. And fewer function calls means faster execution. So how can we do that? Again, question, does anybody recognize this? I know I haven't given you a lot to go on. I figured I'd take a shot at it. Especially since someone said lift A2 earlier.
I would say, go ahead. I'd say function composition, like mapping two different functions versus mapping the composition of those two functions.
Ah, yes. Exactly. This is a functor. A stream is a functor. And there's a functor composition law. And it says exactly what, whoever just answered, thank you. The law says exactly what you just said. If you fmap f and fmap g over something, that's the same as fmap the composition of f and g over that thing. So that's awesome. We can actually do that, right? We can take these two graph nodes and actually combine them by doing function composition on the two functions. And that's what Most does. When it sees that you've put two maps next to each other, it combines them into a single map with function composition. And that was one of the first of these graph optimizations that we implemented in Most. And I have to say it's probably the least interesting, but it was sort of a gateway into thinking about this idea of taking a big graph and making it smaller. And if you're familiar with the concept of monoids or semigroups, you know that they sort of directly represent this idea, right, of taking two things and putting them together and getting a new thing, which is no more complex than the two things you started with, right? It's one of the essential representations of composition in category 3. And it turns out that streams are monoids, and the binary operation for taking two of these things and putting them together is merge. You'll notice it's slightly different. It might be different from what you're used to seeing with a monoid. We allow the union type in the result. That's turned out to be pretty useful. So if you take a stream of A's and a stream of B's and you merge them together, you get a stream of A or B. What if you have also then a stream of C's and you merge that together with your stream of A or B's? You get a stream of A or B or C. Okay, we're starting to build a tree, right? We're starting to build a graph, right? And the graph is starting to get bigger. What can we do about that, knowing that they're monoids? Well, if you think about, if you're familiar with monoids, you know that the operation for putting two things together is associative. And so what that means is you can do these combinations in any order. It doesn't matter whether you combine A and B first, or B and C first, or A and C first. Well, it does matter if you combine A and C first. Sorry, it's associative, not necessarily commutative, but in this case, it happens to be. So if you put A and B together first, it doesn't matter. You can put B and C together first. It doesn't matter. And we can use that to create a different kind of graph. A graph that looks like this, where the merge operation can, instead of building a tree, it can build a list. It can build a list of all the streams that need to be merged and lessen the number of nodes that the events have to flow through to reach their destination. So in this case, in the previous slide, events of type A have to flow through this middle node of stream AB to get to the stream ABC, and then finally get to next step. But in this graph, they only have to flow through one node, the stream ABC node. And we can do this to an arbitrary depth. So if you have a merge tree of any depth, Most.js will flatten that to a merge list of depth 1, right? A merge tree of depth 1, a merge list. And that can be hugely beneficial. That can really squash large portions of the graph if you use merge pretty often. And merge is a pretty common operation. So it turns out this is pretty useful.
Hey, Brian, can I ask a quick question?
Yeah.
So the last example where you were talking about turning adjacent maps into like a single map with functions composed.
Yeah.
That's kind of reminding me of Fusion, like an optimization that the Haskell compiler or GHE does.
Mm-hmm.
I was just kind of wondering, is that like something that you've read about? Was that like an inspiration for some optimizations that you've done?
Yeah, you're talking about stream fusion. Yeah, in Haskell compiler. Absolutely. That's a really cool feature, and it's been a source of inspiration for some of the stuff. You won't find exactly the kind of transformation that the Haskell compiler does in Most, but conceptually, it's been a source of inspiration.
Cool, thanks.
Yep, sure.
I have a question.
Yeah.
It makes a little bit of sense to me, but the combine example from way, way long ago, it seemed kind of similar to merge. Do you want to talk about the differences?
Yeah. Let's see. Does everyone remember that example? Actually, let me switch and do it in the code. Here's an example of combine. Just to refresh everyone's memory, it takes a 2-argument function and 2 streams, and applies the 2-argument function to it. Right, and here's merge. If you think about the 2-argument version of merge, a way to picture that the 2-argument version of merge in your head is, say you had 2 arrays of time value pairs and you did a merge sort on them by the time value. Right? That's a mental model for merge. You still end up with all the A's and all the B's and all the time values of the union of all the times from A and all the times from B. But you get them all ordered now by time, right? So the number of events in the resulting stream is the number of events in the first input plus the number of events in the second input. Combine, go back to, I think this is a great question because they do look so deceptively similar. Combine, as we saw in that example, takes a function from the pair A, B to C. And someone already mentioned this is lift A2. So in order to call F, you need both an A and a B. So something's already different, right? Like merge, if you get an A, you can just propagate it. Or if you get a B, you can just propagate it. But here, we need both an A and a B in order to call the function. So what combine does is it takes the latest A and the latest B and calls the function with them. So let's say you saw an event of type A already, but you haven't yet seen an event of type B, right? And now combine gets an event of type B. Now it can call the function, and it calls the function and produces a C. And then next, let's say it gets an event of type A. So now it has a new A and the previous B. It calls the function with the new A and the previous B, produces a C. And that's, go to that example again. And this is pretty easy to see in this example, right? If I start with, say, 1 and 2, and this is the one, this is my A over here on the left, right? As soon as I get an event, right, I run the function to add the 2 numbers together and it produces a new number. Or if I get a B, right, run the function with the previous value, 12, of A, and the new value of B, 23, and get 35. Did that help?
Yeah, definitely.
Cool. Oh, jump back down here. All right. So the next example of optimization is an operation we haven't talked about yet, but I think it'll be pretty familiar to everybody. Most has these ways to trim off events off the front and the head and tail of the event streams, called take and skip. Take, if you've worked with any sort of list processing library in JavaScript or Haskell or anything, this is a very common operation. So take 10 leaves you with only 10 events. If there were infinitely many, it turns the infinite stream into a finite stream of 10 events, or if there were 11, it lops off 1. If there were fewer than 10, it doesn't change the stream at all. Skip is similar, it lops off the front. A little bit more interesting because these are indexed by time. 10 here is a count. So when you drop 10 events off the front of a stream, the next event, the first event that remains, might still be way out into the future. And we don't change the time of that event, right? These things, if you think about the graph that we drew earlier, the axis that we drew earlier to see how relative time works, you've got time as like an x-axis going horizontally. You can just imagine, right, just like erasing some events off of that graph at the front. And that's how skip works. And it's quite a common operation. Some things that are really useful is like take one. You just want to see, you want to guarantee that you only get one of a particular event. Take one is very useful. Skip one can also be useful. So these are used quite a bit, in fact. They're not exactly monoid operations in and of themselves. But if we change this picture a little bit, and we think about this as pairs of numbers, which in some cases might be 0. So if we look at if you just look at the top set of nodes, take 10, take 5, we can represent that as a new operation called slice, which has two numbers, a skip value and a take value. So slice 0, 10 is the same as take 10. And then on the line below that, slice 10, 0 is the same as skip 10. So we've just taken the two operations and represented them as a single operation that takes a pair of numbers. And once we do that, now we've got adjacent operations of the same type with a pair of numbers. We can start to think about ways we could combine those pairs of numbers to merge adjacent nodes of the graph. And the most obvious thing is if you have a take followed by a slice, or a slice followed by a take, it's pretty easy to envision what's going on. So in this case, you've got a take followed by a skip. And you can just literally transfer the numbers into a new pair, right? The take value and the skip value. And it turns out there's a general form of this where slice S1 T1 followed by slice S2 T2, where the S's are the skip numbers and the T's are the take numbers. There's a simple formula for combining these. It's a little bit, you might think that might have just you might think it might just be subtraction for T1 and T2 or something simpler, but it turns out that min is the right answer for that. And slice, the skip value is via addition. This is actually the monoid operation, the binary operation, if we consider this pair of numbers to be a monoid. And so now we can take arbitrary chains of arbitrary length of skip and take, adjacent skip and take, and combine them into a single slice operation. But what if this is what you need, right? You write this code. Have you thwarted the optimizations? And in some cases, the answer is yes, but in some cases it's not, because there's an observation that we can make about some of these operations, and that's some of these operations, some of these nodes deal with completely independent aspects of the events that they operate, that flow through them. In the case of slice, it deals with the count of skipped and taken events, or if you like, the indexes of the events. And map deals only with the value. It doesn't care about the time. It doesn't care about the index. It doesn't care how many things have been taken or dropped. It just deals with value. And so those two operations, slice or take and skip, and map, are independent. And when you have that situation in the graph, it turns out that you can commute those operations. And so you can do this. You can start with this map, take, map, skip. And in the first step, you can commute all of the takes and skips to the left past the maps, and all the maps to the right past all the skips, past all the takes and skips. And now you end up in a situation where you can apply the optimizations that we've already seen. You can combine all of the takes and skips, and you can combine all of the maps. So you can take this chain, which seemed like it was defying optimization, and actually optimize it by doing commutation on parts of the graph. So you might ask yourself, couldn't I just write the code that way in the first place? And the answer is yes, but the kind of knowledge you would need in order to do that doesn't scale very well. In order to do that kind of stuff manually, you need to be able to know what the graph looks like. And in a case, here's a case, it's totally contrived, but I think it represents the idea pretty well. In a large system where you want to be able to freely write the functions you need, you might not know or might not want to structure your functions or the kinds of functions where you expose all of these things in a way that makes it obvious that there are skips next to takes and maps next to maps and merges next to merges, right? And if you look at the last line of this code, you would never know, right? There's no way that you would know if you hadn't written all of these functions. If you extend that out then to larger applications where other people are working on them, right? Are you going to like confer on every one of these operations to make sure that you're putting them in an order where you can manually combine them. Are you going to look for those opportunities? And it would be much nicer if this happened automatically. And that's why these optimizations are built into Most.js, is so that you can focus on doing what you need to do, right? Write the application code you need to write, and let these optimizations do what they can for you to make the graph smaller so that you get the best possible runtime performance. Now, it's not perfect. You know, it can't optimize everything. It can't fix also, you know, all manner of performance problems, but it is one aspect of performance that, you know, you no longer need to worry about, and you sort of get for free when you use Most.js. So that's kind of it for you know, a lot of the material on Most.js itself. But I did want to kind of leave with these last few slides. Going on, you know, maybe close to 10 years now from where it started, I've learned a ton about many things from working on this project. But two of the things I wanted to try and highlight in this presentation. One is that architecture matters. We've been able to do a lot with a very compact, simple architecture. And that came from, number one, starting with goals. We had some goals in mind, and it took a while, but eventually we found an architecture that let us achieve those goals. You know, it's very modular. It has very predictable and consistent behavior, even when you're refactoring graphs, and has excellent performance. So this has been really great to see. I've always been a fan of software architecture, but working on Most has really showed me, you know, that it can go, that thinking carefully about architecture can go a really long way. Another is simplicity, and simple is hard, but it's absolutely worth it. I don't think it would be any much fun working on Most.js if it didn't have the level of, you know, the simplicity that it has, that the architecture has. There are some complicated implementations of operators in Most.js, and namely the scheduler is very complicated. You know, more complicated than it needs to be. But in the places where it's simple, it's really fun to work on. It works really well. But it wasn't instantly that way. We didn't just wake up one morning and say, aha, I know exactly the right architecture to build a highly performant reactive programming library. And here it is. This was, you know, years of failing, to be honest, you know, making things that didn't have these characteristics, that wasn't simple, wasn't performant, wasn't fun to work on. Well, maybe it was fun when we started, and, you know, after a while started to show some of the problems and wasn't fun anymore, or didn't hold up to use cases anymore. But I can say now it was absolutely worth it to go through that process, and the whole time focusing on, you know, asking the question, how could this be simpler? And if you've seen Rich Hickey's talk on Simple Made Easy, I'm not talking about easy, I'm talking about simple, especially in his in the way he presents it. And then finally, math. Math is something It's actually been a part of my whole life. Literally, my dad is a math professor. He just retired, so I guess I can say, you know, he was a math professor. But you know, I kind of, when I started programming, I didn't really think about it as the tool that it is. And I think that happens a lot in the industry. You know, from what Tyler has told me about SimSpace and use of functional programming there, the kinds of questions you've been asking and the kinds of answers, you know, throwing out lift A2 and understanding what monos are, you know, it sounds like SimSpace, you know, has embraced this, and I think that's awesome. But it's been a revelation for me to come back to abstract algebra and category theory and just arithmetic and simple geometry and things like that, because they're really great design guides. And math is a language for, you know, describing the universe, and when there are similarities, math finds them. And so, you know, a lot of the design in Most.js, when I started realizing that, you know, math was useful and important, started to take a turn. We started to see things like these opportunities for optimization based on monoids. It's probably not something I would have thought of before I came back and started looking at it with my math glasses on. It's also a great decider. There's a lot of opinion in technology communities about what's better and you know, what does better mean even. And a lot of times math can help answer those kinds of questions, you know, without resorting to opinion. It can't answer them all, but a lot of times, if you can find a mathematical solution or a mathematical route to a solution, it works out really well, because it takes that the subjectivity, a lot of the subjectivity out of it, and can really lead you to a good solution without bias. And that's pretty much it. I do want to say thanks to these three folks, Frederick, Tyler, and David, who are all members of the Most core team. Like I mentioned in the beginning, they really are impetus for the existence of Most core in the first place, and you know, have really contributed a ton. So thanks to them. And thanks to all of you. Again, this was a great opportunity to present some things that I've never presented to an audience before. We talk about them, the Most team, a lot, but having the opportunity to talk about them with all of you is really cool. So give it a try. And there's links here if you want to learn more. Links to the examples. We also have a GitHub org for community members. There's a lot of community contributions there for stuff that the core library doesn't provide. There's also pretty good docs, we think, much better than 1.0, than most 1.0. So check those out, especially the concepts section, the doc where it talks about events and event streams. I think that's probably pretty interesting for folks. That's all I got.
Thanks, Ryan. That was awesome.
Yeah, that was really good. Do you have a few minutes for questions, or are you open to questions?
Yeah, I have. Yeah, I have time. Feel free.
Okay. So I've been following your libraries for quite a long time, and I noticed that. So you've mentioned Haskell on the call a few times, and I've noticed that I believe even before you started getting into working with Flow and TypeScript, you always kind of annotate type signatures using the Hindley Milner like Haskell style type signatures. and you said you're aware of Stream Fusion and various things related to Haskell. So I'm just curious, like, what is your relationship with Haskell? Like, have you ever used it professionally, or is it just been like an interest for a long time, or?
Yeah, great question. I've used it professionally very minimally. I didn't even know Haskell existed until about 2012, interestingly enough. And I might have mentioned that earlier at the beginning of the presentation. And when I first encountered it, I think I probably had a reaction like a lot of other people do, like, what is this? Where did this come from? How have I never heard of this? Does anybody use this? Is this a real language, or is this, just a toy for academics? And the more I started learning about category theory and coming back to math is when I really started to take an interest in Haskell. Funny story. I remember one of the moments when I started thinking more about category theory and math. Back in around that time, 2012, is when promises were coming to JavaScript in user land form, and this was before they were part of the language. And I wrote a gist that was a proof that promise was a monad. Funny thing was, the proof was wrong. and there was some mathematician who called me out on the comments of the gist and made me realize that I actually don't know what the heck I'm talking about. I thought I did, but I didn't. And that interestingly enough, caused me to want to learn why I was wrong. And that led me back to learning more about these algebraic data types and type classes. And I found in Haskell these ideas were represented so clearly that I really took an interest in Haskell. So it's been a personal interest. I've written a good bit of Haskell myself personally. I did have an opportunity to use it professionally for a short period of time a few years ago. I found it difficult to apply in gunky real world situations, and mostly I attribute that to my not having used it enough in those situations.
Cool, thanks. Yeah, I was just curious because I could tell that you had familiarity with it, but I wasn't sure, to what level. And our backend team here uses Haskell, so that's why I was interested. But yeah,
cool. Yeah, Tyler mentioned you all have quite a large contingent of Haskell developers.
That's true. I did have one other question. I don't know if anybody else does, but near the beginning, you showed a slide of other libraries, like third-party libraries and extensions and whatnot. And one of them was Most behavior, dealing with behaviors like continuous time.
Yep.
Which is kind of more reminiscent of like real FRP. I've looked at that library and played with it a little bit, and I think it's really cool. I'm just curious. Even I think like yesterday or something, we had a chat in Slack where a few of the backenders were kind of discussing the pros and cons of different reactive programming libraries, and how often continuous time is really useful versus just discrete events and just like reactive programming with events. And the one case that I've seen where it can be really cool is like dealing with animations and having the time value affect the animations in interesting ways. But I struggle to come up with like other use cases. So I'm just curious, like, what have you built with it, or like what kind of things do you find it useful for?
It's a great question, and I'll be completely honest. I haven't found any compelling use cases in my own work and in my own exploration that seem like aha moments. Like, aha, this use case is solved by continuous values. and I can't solve it any other way, or this is absolutely the best way to solve it. But there are lots of areas where I haven't done any work, so there are probably situations where they are useful. I know the history there. Going back to Connell Elliott, his original conception of FRP, he came from the animation world, and so so in his original formulation of FRP, there were events and there were continuous values, behaviors, and one of the things that I know that they were used for in animation is it decouples being able to talk holistically about for example, the path of something through a scene. It decouples that from any sort of resolution, right? Time resolution, and then you can build a behavior that represents the objects in your scene without worrying about time, and then you can sample that behavior with something that represents time, right? Like an event stream that's periodic on 30 times a second or 60 times a second, and that allows you to decouple the scene itself and the building of it from the rasterization to some display device that might be operating at a particular refresh rate. So that was one of the original uses for it. I've built a couple of things that do that. It's really interesting and it's kind of fun, but in the kind of work I tend to do in my day job, I've never run into a case where I've said this calls for a behavior. So I guess it's a decoupling mechanism around time is a great way to look at it.
Cool, thanks. Yeah, I kind of feel the same way, but that was still an interesting answer. I think somebody in the chat just asked a question.
Okay, let me take a look.
What about the ability to replay a slice of a stream?
Are you asking, does Most.js provide that?
I was just, maybe it wasn't a not well thought out comment, but I was thinking along what Josh is asking about the usage of time, and my thought process was that you might want to reach in to a particular stream and replay a certain part of it, and the only way to do that is through time, not just discrete events.
Yeah, yes, it's a good question, and stuff like this comes up a lot, actually, when people are trying to solve real world problems. Sometimes events get missed, and they want to know if they can replay them. But in general, the way I think about it is that you would be duplicating the events and just rooting them at a different time. So you could preserve the durations between the events, but you'd be changing the absolute time value, the global time values of those events. I think it can be a useful thing to do, but also it can be a little bit of a problem whenever you're messing with time or changing the time of events in ways that are hard to reason about. So I think in some sense, it depends on the use case. You can do it, but be careful. There are actually operations that do change the time in Most.js. There's delay, and then there's also concat map, which is a little bit of a weird thing. I'm not convinced it's actually a good thing, but but it's there. Did that help? I feel like I maybe didn't answer your question, but I hope that helped a little bit.
Yes.
Okay, cool. Let's see. I see
I have a
someone
question.
raise their hand.
Yeah. Yeah, first of all, thanks so much for the talk. I hadn't heard of most before this, but it seems really neat. So anyway, so I've done some like FRP programming in Haskell. But I guess when thinking about the JavaScript side, like this is a really like powerful general purpose library. But obviously the dominant player as far as like reactive rendering in JavaScript is React. And I guess with the React, it's just a bit more opinionated, basically saying that you don't need all that power. You just need one basically node in your graph that renders all of your UI state into the HTML. So like, would you see, do you use Most, I guess, as like slotting alongside React, or maybe React handles the rendering output, but Most would handle more the input side, which can be more complex? Or would you just replace React entirely with Most? Or maybe what advantages does Most have over that other approach?
Yeah, great question. Very practical question too. And so the way I use or have used the two together is to do what you said, to build input and then transformations and behavior, network calls, whatever, using a Most graph, and then just use React on the render, the output, screen output end of that. And it works great. To do MVC example that's linked in the at the end of the slides is built that way. It feels like, so if I'm honest, I like using React that way instead of as a holistic application framework. And for me, that setup works really well because it's how my brain works. So I think that is one valid approach. I think there are people building applications in different ways. So, you might want to look around at other ways people have approached that problem, because I don't know how everybody's doing it. And I'm sure there are some interesting and valuable things that the community's done.
Okay, thanks.
Yep.
Yeah, Access, somebody linked a library called Cycle.js that you might want to take a glance at later.
Okay, cool. Will do.
Anybody else have any questions?
I have one more if no one else does. I guess my other question is, one other thing I've found, again, on like the Haskell side, is that initially when doing FRP work, I ended up with a lot of nodes. And then eventually I trimmed it down, not to one like React would do, but kind of like just basically one node per sort of independent state value. And so then for my, whatever small to medium sized game, it would be on the order of like 6 or 7 nodes total, I guess. Have you, I guess, what opinions do you have on like when something should be a node versus just kind of like a purely functional value? Or like how big should a node be in a sense? Does that make sense?
Let me think for a second. So I guess one thing I've noticed about using Most and about using a lot of any library in JavaScript, where the primary programming approach is to assemble bigger things from really small things, is that if you're not careful, you can create code that's really, really hard to understand and refactor. And types help. TypeScript or Flow helps a lot, because at least you can't do the wrong thing. But sometimes it becomes unclear what it is you're actually doing. And sometimes it's just simpler to write some plain old functions and do it that way. Or sometimes it's even simpler to go full on imperative and write a function with statements. And I think they're all valid. I think it's, knowing when to do what is the hard part of that. I like having all those tools at my disposal. And so I'm very comfortable assembling large Most graphs, but other people may not be as comfortable. And it may be the right thing to use large function body maps, for example, to do a lot of work, or flat map or switch, something that allows you to return a new stream and have it merged so that you can do even more work, or concat map can be useful for HTTP requests. So I think it's more about, what are you comfortable with? What is your team comfortable with? And what is the best approach for the kind of thing you're building? Just to give a quick example of a similar situation, a few years ago, I worked at a company and I was like super gung-ho on functional programming in JavaScript. And I was gonna, bring this idea to the team with types and Lambda, and we were gonna do function composition everywhere and point free, and we created an app that worked great, but my God, was it hard to refactor. So we created something that worked well, but it was just difficult for the team to work with, even though we had types. And in my current job, my team is not at the point where they are comfortable with that kind of thing. And so knowing that, we write code that's more statement-based. We try to apply functional concepts like immutability and referential transparency wherever possible, but the code we write is very straight ahead, imperative code a lot of the time.
Thanks.
Yep. I think I saw, was there another question in the chat? I think I answered it. Okay, cool.
Thanks a lot, Brian. That was really good.
Yeah, thank you so much.
Great. Glad everybody enjoyed it. I certainly had fun presenting this stuff. Like I said, it was first time world premiere. So thank you all. If you use Most.js, feel free, reach out.